This is CPM Calculus Chapter 3, number 188. So let's go ahead and graph y is equal to x to the 2/3 power. I'm not going to use graph paper, and I'm going to kind of sketch it. Okay. So we know there's the axis. We know that it looks kind of like this, right? Like a bird. It hits our origin, 0, 0. It goes to the right 1 and up 1, left 1 and up 1. And this is what it looks like. Okay, you can use a calculator to graph this if you're not sure how to. Or you can use points. You could plug in -1, 0, 1, 2. You can plug in different points. So let's sketch the derivative of y, dy dx. I'm going to use green color without a calculator. Okay, so from -infinity to 0, we are decreasing, right? We're going down. So that means the derivative is going to be from -infinity to 0, right? Our function y is decreasing. That means dy dx is going to be negative. Also, from there to there, we are concave down. Well, actually, I'll talk about concavity in a second. From 0 to positive infinity, y is increasing. Therefore, our derivative is going to be positive or greater than 0. Our concavity, from -infinity to positive infinity, it's concave up, right? And what that's telling us is that we are always going to be increasing. So y is concave up, so dy dx is increasing. Okay, so over here it is, oops, did I say concave up? These are both concave down. My bad, right? They're both concave down. Y is concave down. So dy dx is decreasing. All right, that's going to change it from what I had it in my mistake. So over here on to the left of the x-axis, right, we have it being negative, our dy dx, and it decreasing. So we want it to be decreasing and negative, and it's always decreasing, right, up until, I don't know, until forever. Right, so we want it to be going down. Let me draw it a little better. Basically, we want it to go down here, right? It's still decreasing after we pass the y-axis, but now we are above, we're positive, we're above the x-axis. So we're going to be decreasing, we're going to start high and then go low, okay? So this is kind of what the derivative function is going to look like. So what happens to our derivative at the vertex? At this point, we're right here. What happens to our derivative at the vertex? Well, we can see that from the left, right, we're going down, 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 down. So limit as x approaches to 0 from the left of our dy dx, of our derivative function, it's going to be what? It's going to be basically it's going to be a big negative number. We could even say negative infinity maybe, right? It's approaching down. As we're approaching 0 from the right of our derivative function, right, we're going up to the left from the right, we're going up. It's approaching positive infinity. So what happens? Well, then we know dy dx, let's just say y is not differentiable, right? Not differentiable at x equals to 0 then, because when we take the limit from the left and the right of our the derivative, it goes to a different place, okay? Therefore, we do not have a derivative. Dy dx is not defined at x equals to 0. Okay? So that's part A and B. Let's go on to part C. Part C says use your calculator to find the slope of y is equal to x to the 2/3. So let's bring our calculators out. All right. Oops, let me move it over. Sorry about that. Okay, so let's go ahead and graph y is equal to x to the 2/3 power. Graph it, and you're going to see, yep, it looks like our, I don't know, I used to draw seagulls like this. And then let's find what the derivative is using our calculator, okay, to find the slope of this function at the vertex. So let's, F5 will allow us to do the math. Let's go down to derivatives, dy dx at 0. Okay, at x equals to 0, what is my derivative? No solution found. Yay, escape. Okay, no solution found. No solution on my TI-89, right? Let's go ahead and try to find it over at, I don't know, 0.1. Right, x is 0.1. Let's find it. Oh, I think it just said it. Let me do it one more time. Number 6, number 1, at x is 0.1, and it says it so quickly, right? The derivative is there. You go over to the right, we have a derivative. Okay? So, in fact, let me go ahead and change my answer. I'm not going to say it's positive and negative infinity. I'm just going to say, for part B, I'm going to say a negative number and a positive number, because it doesn't look like it's necessarily going to positive and negative infinity. It's just a positive and a negative number, but still, since they are different, it's not differentiable. Okay, so let's go back here. No solution on my TI-89. This should be the case. At x equals to 0, no solution, right? Because we already found out it's not differentiable there, so this should produce no slope, right? We saw different places that it has a derivative, right? We could do one more. Let's check it at -5. Okay, it has a slope there, right? All right. So some calculators, though, let me see. Let me bring out the TI. Let me bring out the TI-83. Okay, if we graph this here, x to the power of 2/3, because our calculator is just really advanced. The TI-89, we graph it, okay, there it is. Whoa, it's kind of slow. Come on, buddy. All right, and then we go to second, calculate. All right, and let's go ahead and calculate the derivative dy dx at x is equal to 0. Yeah, enter. And it's saying there, yay, it says dy dx equals to 0. So I can go ahead and say TI-83 plus says dy dx equals to 0 at x equals to 0. Okay? So that's something that you might want to take a note of. Our calculator is pretty advanced. It has some smarts to it. Okay? So let's go into part D. Part of the reason most graphing calculators incorrectly determine slopes at the vertex of an absolute value graph, as well as other cusps, like this one has a cusp, right, is because they use the symmetric difference quotient to calculate the slope at a tangent. Okay, so for example, for f of x is equal to the absolute value of x, they use f of x plus h minus f of x minus h over 2h, right? So they're going to use the left minus the right, right? Because that's one definition, right? When you use the limit as h approaches 0 of this, right? And you have it over 2h. Or you can use f of x plus h minus f of x over just h. But this, they're using x plus h on this side, and x minus h on this side. So that's how most calculators do it. Okay, so let's go ahead and use their method to find f prime of 0 for h is equal to 0.1, negative 0.1, and 0.001. Not 0, 0, but just 0, 1. All right. So let's go ahead and do it. F prime of 0. Right? If we use this function here, it's going to be f of, well, x is 0, so it's 0 plus, and this is going to be h is equal to 0.1. F of x is f of x plus h is f of 0 plus 0.1 minus f of 0 minus 0.1 divided by 2 times 0.1. All right, so that's just f of 0.1 minus f of negative 0.1 over 2 times 0.1 is 0.2. Okay, so what is f of 0.1? Well, we're using the absolute value function, so it's just going to keep it positive, minus, what is it again? Positive again, over 0.2. The numerator then becomes 0, and that's equal to 0. All right, so f prime is 0, it gives us 0. F prime is 0 using h is equal to 0.1, negative 0.1. Let's go ahead and plug that in. That's 0 plus negative 0.01. Oops, plus negative 0.1 minus f of x minus h, x minus negative 0.1, right, over 2 times negative 0.1. Okay, so again, that's just the same as f of negative 0.1 minus f of positive 0.1, because these two cancel, over negative 0.2. The absolute value function just keeps these values positive. So again, we have 0 over something, it equals to 0. Okay, so you see how if they're using this method to just approximate it, our calculator is smart again. It doesn't really approximate it. It gives us the exact values, right? So let's try it again. F prime of 0, and let's get smaller, right? So let's use h is equal to 0.001. So this is just f of, we're using x, right? These are all for x is equal to 0 plus 0.001 minus f of 0 minus 0.001 over 2 times 0.001. Actually, it's 0.01 it should be, but let's do this one. It's even smaller. It's going to make a case, right? Minus f of negative 0.001 over 0.002 when you multiply 2. Again, the absolute value function is just going to make this 0.001 minus 0.001 because the absolute value of negative just is positive, the same value. So that's 0 divided by whatever number we have, and it's 0. Okay. As h gets infinitely smaller, as h approaches 0, right? This is always going to be the same thing. It's always going to be 0 in the numerator, right? And therefore, it's always if we're going to estimate it with some value of h, right? As h is approaching 0, but not 0, we're always going to have 0 as the output, and our estimate, f prime of 0, when f of x is equal to like our absolute value function, using this method is always going to be 0. Even though we know, right, this is the absolute value function, we're going down here, the slope is negative 1, right? On this side is positive 1, and so at the point in the middle, the vertex, it is not differentiable, right? Should be not differentiable at x equals to 0. So f prime of 0 should be not defined, right? All right, so what leads our calculator to make the mistake? Well, our calculator, since it's just using this method, right, well, actually our calculator doesn't, but some use this method. If calculators use this method, because there is this symmetry, right, this evenness about these functions, so when you look at the left and right side, they're going to cancel each other out. So let's go ahead and say that. Calculators that estimate or approximate the slope using the symmetric difference method of the derivative, right? They basically get tricked by symmetric and even functions, right? Well, some even functions do have a derivative, like x squared, right? But even functions, by symmetric even functions with cusps, right? All right. So that's the explanation for why some calculators get it wrong, like the TI-83 and many others. For ours, again, the TI-89 is pretty awesome. It's more reliable than others, but it's not perfect. All right, that ends CPM Calculus Chapter 3, number 188.